Hi, my name is Andrew Keezer, and I'm a senior biochemistry student at the University of Massachusetts Amherst and an undergraduate research assistant in the lab of Dr. Kathleen Arcaro. For over a year now, I have been assisting in a study focused on testing a new method for determining an individual's breast cancer risk. In this video, I'd like to talk about our research and about the importance of assessing breast cancer risk accurately. Breast cancer is the second leading cause of death in women, resulting in over 40,000 deaths per year in the US alone. And even though it's so common, it's often difficult to predict breast cancer risk due to the intricate nature of the disease itself. And although family history can be revealing of risk levels, nearly 70% of cases are considered sporadic and aren't related to family history of the disease. The current method for predicting breast cancer risk is called the Gale model. This is a survey that takes into account factors such as age, ethnicity, medical and reproductive histories, and immediate family history. And although this list may seem comprehensive, it has only a 56% success rate in predicting future breast cancer cases. In order to increase accuracy, more personalized biological tests must be developed in order to actively assess one's unique breast cancer risk. More accurate risk assessments could lead to early detection by identifying individuals at high risk for developing breast cancer and encouraging them to participate in more frequent cancer screenings. And in many cases, early detection increases survival rate drastically. Therefore, it's absolutely necessary that we develop new ways of determining an individual's breast cancer risk. Our project aims to examine DNA for markers of breast cancer risk. DNA is often described as the instructions for life, and many changes in these instructions have been associated with increased risk of different cancers. In particular, we will be comparing specific markers in the blood DNA of women who have developed cancer and those who have not. The DNA we will use for our study was provided from a prospective study conducted by the National Cancer Institute. Participants in prospective studies provide annual medical information and samples such as blood over extended periods of time, so that if they are eventually diagnosed with a disease, scientists can examine the previously collected samples to essentially go back in time to see what changes in DNA, if any, might have been predicted of the disease development years before diagnosis. Our prospective samples come from 300 women who developed breast cancer. We have 2 samples of DNA from each woman. One sample, 4 to 7 years prior to diagnosis, and another 1 to 2 years prior to diagnosis. In addition, for each woman who developed cancer, we have 2 DNA samples from a matched control, which are women of comparable ages but did not develop cancer by the same time point. We have been using state-of-the-art DNA sequencing technology to examine 5 specific markers that have been shown in a previous study to possibly be predictive of breast cancer. By using a newly developed method to analyze our large collection of samples, we hope to confirm the predictive ability of these DNA markers and pave the way for a new blood test to predict breast cancer risk. Because informing individuals of their particular risk levels empowers them to make more informed healthcare decisions and allows those at particularly high risk to seek assistance years in advance of breast cancer diagnosis.